we have mentioned Leibniz's theorem in which in the integral form in which we calculate a function by carrying out the integral of the function and then differentiating it with respect to the time. It's a very simple form. The theorem is used to help us in the applications of Reynolds transport theorem applications, and therefore this is very simple equation as compared to the differential manipulation that we have to do, which is sometimes very tedious. But the Leibniz theorem in its integral form renders it very simple, as we see with a simple application to start with. The example here is that one-dimensional Leibniz integral reduces the following expression as far as possible. F of t is equal to the function capital F is equal to derivative d by dt of the integral e to power minus x square dx from the lower limit, which is x equal to 0, to the upper limit, which is x equal to capital C some constant times t. And therefore we can see that this portion will turn out to be some function of t. And when we differentiate it with respect to dt, we will have a function which we denote by f of t equal to d by dt as given. Now, when we try to solve it and we try to reduce this function as far as possible by using this theorem, then we see here that the function g is this much. G of xt is here equivalent to e to the power x square. So we apply the theorem, and when we apply, then we replace g of xt by e to the power minus x square. And you can see that g is not a function, the capital G is not a function of time, it's only a function of x. When we integrate it, the integral of e to the power ex square, we need to calculate it, and how simple it is. You can see that the function using this equal to d by dt equal t equal to 0 to t equal to ct e to power minus x square into dx will be equal to, by using, here we are using the Leibniz theorem. This is a to b dg by dt, and g is e to power x square. So this will be e to power minus x square plus, we don't have to touch the function, we simply differentiate the upper limit into, and for the function, in the function we replace x by its value, the value of x by whatever the value of the limit is, and we leave it as time, and then minus the derivative of the lower limit into the function g, which is at lower limit a and t. When we calculate it, since there is no function, there is no variable t involved in capital G, and therefore partial derivative of the function e to power minus x square with respect to time t will be 0. So the contribution coming out of it is 0. We substitute here the upper limit instead of carrying out any differential or integration, and just by substituting replace x by b, so we will have e to the power minus b square and then db by dt. So when we do, so since b is equal to c into t, then db by dt is equal to only c. And therefore, you have here c into e to power minus b square. In the lower limit a, there is no t occurring there. Therefore, when we differentiate a with respect to t, it will be 0. So the contribution coming from this is 0. Here the lower limit is replaced, x is replaced by a, but it doesn't matter because whatever this may be, when this is being multiplied by 0, we are getting 0. In the end, what are we getting? This whole function is reduced to this quantity in the square. So you can see that instead of carrying out a very complicated integral in the form that it was given, then that normal integration will take a lot of time and hard work. But using Leibniz theorem renders it very simple, and you can see how easily we can calculate the value of the function. Similarly, we can generalize the one-dimensional motion, the one-dimensional integral format of Leibniz theorem to three-dimensional form, which is given here, and the numbers here are referred to the book that we are following. And all this helps us in the application of Reynolds transport theorem. And you will recall that I mentioned that Reynolds transport theorem provides us a smooth linkage between the Eulerian system, between the Lagrangian system and the Eulerian system. And you can see here, we consider here at a time t equal to 0, the control volume and the material volume are at the same place at the time equal to 0. But at some time t plus delta t, t plus a small variation in time, the values, these values then changes. And they are not the same, they are not the identical, and therefore they will have some non-zero values. And similarly, an equation can be worked out in the same form as we did last time. In the one-dimensional motion, similar computation can be calculated in the three-dimensional motion. If we try to solve it as we did last time, then the equation that we get and the final values that we obtain are here. And this one.